All right, statisticians, right now we're going to get into really the only deep conceptual aspect of this week, and it's the power of a test. And you got to love statisticians who think they're the Avengers talking about the power of a test and the degree of freedom and all this dramatic language and stuff. But the power of the test is actually very, very interesting. And it's not assessed in a very difficult way, but its concept is deep and can sometimes be challenging. And it's actually connected to the idea of making errors, really. And in fact, the power of a test is really all about not making error and the probability of not making a certain kind of error. So remember that there was two kinds of error. We talked about type 1 and type 2 errors. And for instance, a type 1 error was alpha, and that was the probability of making a type 1 error, right? And so if alpha was, for instance, 0.05, there was a 5% level of significance, then the probability of not making that error would simply be, well, 95%. And that's not the kind of error that we're worried about when we're worried about the power of a test. The power of the test is actually connected to beta. And remember, beta was the probability of a type 2 error, right? And so we're going to see that the power of the test is the probability of not making this type 2 error. And that's its definition. So let's just jump right to it and try to figure out what affects the power of a test and actually how to calculate it, because calculating beta gets a little crazy. All right, so let's start with this, right? Remember that beta was the probability of making a type 2 error. And in general, the type 2 error is talking about the probability of failing to reject the null hypothesis when the alternative hypothesis is true. So for instance, if we were doing some kind of test where, let's say, the null hypothesis was that mu is 40 and the alternative was mu was less than 40, we made a type 2 error for instance, if mu was actually less than 40, theoretically. And we'll talk about this exact example in a second. Let's say mu is actually 39 and not 40. And therefore, the alternative hypothesis was in fact true. It wasn't less than 40. And so if we failed to reject the null hypothesis, we made a type 2 error. So the power of the test is really the probability of avoiding this, right? The power of the test is going to equal 1 minus beta. It's the probability of not making a type 2 error, right? It's the probability that we correctly reject the null hypothesis. And if the null hypothesis is false, then we definitely want to reject it. And so the power of the test basically describes how likely we are to reject the null hypothesis. So in this instance like this, we notice that, say, 39 is definitely less than 40. Then it seems like, yeah, we should have definitely rejected it. But how easy is it going to be for us to reject the null hypothesis if the truth is just that that mu is 39, right? And so there's three things that are actually really going to affect the power of a test, and three ways that we can increase the power of the test. So this is really what you're assessed on an AP Stat, and I want to reveal those right now anticlimactically. And here you are. What are the three things that affect the power of the test? Shazam! That's we talk about the level of significance, the sample size, and the effect size. And the effect size is a little bit weird. We'll talk about that in some detail in this video. Hopefully we'll have time. We won't have to go into too many additional videos. So what will increase the power of the test? Well, first, that you will increase the power of a test if you increase the level of significance, right? And so remember, say we tested something at 0.05, right? That meant there was a 5% chance of a type 1 error, right? But if we wanted to decrease the probability of a type 1 error, we'd actually have to have a smaller alpha because you wanted to avoid a type 1 error. In this case, if it turns out that the alternative hypothesis is true and it would be an error to fail to reject the null hypothesis, you want to make it easier to reject, right? You want to make it easier to reject if you want to avoid a type 2 error. And so that to make it easier to reject, you should increase the level of significance. Do something like alpha equals 0.10. Now it's easier to reject the null hypothesis. It's going to be that decreases the beta, the probability of a type 2 error, and as we'll see, therefore we'll increase the power. We have more power if we use a higher alpha. What else? Increasing the sample size. Now, in a very intuitive sense, whenever you have simply more data, more good data, then just having more data should always give you a better way of being able to detect that, in fact, the alternative hypothesis is true. There's also mathematical reasons that have to do with the amount of variation in a sampling distribution that changes with sample size. We know that as the sample size goes up, then the amount of variation goes down, right? And so as n increases, then the amount of variation in the sampling distribution, right, it decreases. They're inversely related like that. And so in that sense, we'll be able to get more power out of our test just by having a bigger sample size. Now, the last thing I have listed here is the effect size. That thing seems kind of weird, and we're going to really need to see an example to really fully get it. But the effect size really has to do with how incorrect our null hypothesis is, right? So, for instance, when we said mu equals 39, if mu equaled 39 in reality, but the null hypothesis was that mu equaled 40, well, 39 is less than 40, but it's not a whole lot less. So in this sense, we could say that the effect size was -1, right? And when we talk about increasing the effect size, we think of it almost like an absolute value, not increasing it exactly numerically. So in this case, like we were off by 1, right? But if let's say the truth was more dramatic, let's say the truth was 38, well, then the effect size would be the effect size would now be equal to -2, because this is 2 away from the null hypothesis. So the idea is the more and more true the alternative is, in other words, the greater the extent to which the null hypothesis is false, then the easier it should be to reject the null hypothesis, and therefore we'll have more power in our test, right? So if our null hypothesis is really wrong, then we should have an incredibly powerful test. Almost at any level of significance in any sample size, we should be able to reject. However, if the null hypothesis is only off by a little bit, like say 39 versus 40, it's going to be a less powerful test. And so this is in general stuff. Let's flesh this out. Let's kind of look at these exact kind of values and put them in context of an actual kind of problem. And then we'll actually look at an essence of how to calculate power, though in another video I will calculate power and beta with you and all that. So let's put these numbers that I was just mentioning in a context. Let's say, suppose we carry out a test of significance at alpha equals 0.01, right? And where we're talking about, in this case, mu all along, it's been the true average highway gas mileage of the 2012 Hyundai Accent. Pull back the curtain, I actually bought a brand new 2012 Hyundai Accent, and when I bought it, they told me the average highway gas mileage was 40 miles per gallon. I bought it thinking that. Later on, it kind of came out that, in fact, maybe they weren't correct. Maybe their claims were problematic. And so let's say we actually were at the edge of discovering that, in fact, Hyundai had some problems with their claims about the gas mileage of their cars. And so let's say we collect some data. We collect from a random sample of 30 cars, and we find a sample mean of 38.9. And let's just suppose, because, hey, it makes life easier, let's suppose we know the population standard deviation is 3.1. If we actually carried out a test based on these data, we could put in our calculator and verify, in fact, it was true, but you end up getting a test statistic of -1.944 and a p-value of 0.0260. And when we were given a level of significance of alpha equals 0.01, so what would we decide to do in this scenario? Reject or fail to reject? In this instance, we would fail to reject the null hypothesis. Why? Because we had a very, very strict level of significance. For instance, Hyundai is not going to be too inclined to say that they're not telling the truth about their gas mileage, and so they might demand a very high level of significance to avoid a type 1 error and say, oh, your average gas mileage of your cars is less than 40, when in fact it isn't. They'd want to have alpha equals 0.01. In that case, we would fail to reject. But let's say, and actually this came out to being the case, let's say just theoretically that their gas mileage actually was less than 40, right? Like I said before, let's just suppose that it was 39, right? If the reality was 39 and therefore it was less than 40, then we should have rejected, right? But we didn't. We made a type 2 error. Right? And now when we talk about beta would have been the probability of us making this type 2 error. What was the probability? That would have been beta. And then the power of the test, let me get another marker out here. The power of the test, would have simply been 1 minus the probability that we could have avoided this type 2 error. Now, one of the issues with calculating beta that's very different than alpha. In alpha, you just basically pick alpha by setting a level of significance because you assume the null hypothesis was true. You assume that mu is 40. To calculate beta, you need to know the truth in some ways. For instance, you need to know that, in fact, the alternative was true and maybe was 39. But that's kind of a problem because in order to calculate beta, you have to know the truth. And if you actually knew the truth, then why are you doing a significance test in the first place? Funny story. Do you only calculate power retrospectively? Like, ooh, you did a significance test and then later you found out the truth and you're like, ooh, what really was the power of my test, as if it was like this fun academic thing. And reality is, no. If that's all that power was this academic exercise of reflecting back based on when you actually did find out what the true value of the parameter was, then that wouldn't be terribly useful. Instead, what we might do is think about hypothetically, right, and more hypotheticals, but hypothetically, like what would be the power of the test if mu was 39? And you might wonder, what would be the power of the test if mu was 38? And what would be the power of the test if mu was 37? And so on. And you could actually come up with an equation to describe all this kind of stuff. And why do we worry about this? Because maybe we're worried about some kind of effect size, right? Maybe we're saying, I really want my test to be powerful if the truth is 38. Or I really want my test to be powerful if the truth is 39. Or I really want my test to be powerful if the truth is 37, etc. It all depends on how big of a difference between the hypothesized null. Hypothesized null hypothesis. What's going on there? The hypothesized value and what kind of values would be important for us to be able to detect. And so you can, in this kind of way, hypothetically think about the power of a test by saying, how powerful do I want my test to be if this is what the truth really ends up being? And so mathematicians will decide on the level of significance. They'll decide on the sample size based on how powerful they want the test to be for a given effect size. All right. So let's actually see the power of the test. And this isn't the true full calculation. In another video, I'll laboriously walk you through all the steps, but this is kind of fun. In order to calculate the power of these tests, I actually use Geogebra, and I did a bunch of stuff in the computer. If we were in class, I'd play with sliders, and you would see that these normal distributions are moving and be like, ooh, this is so fun. But here I just printed out some pictures because I thought that these static images could actually be just as good. So what the hell, excuse my language, what the heck is going on here? Well, let's say that let's first look at this distribution right here, which I'm now shading in green, right? And this is the distribution that's ultimately based on the null hypothesis. Notice where it's centered. It's centered right here at 40, right? And so the null hypothesis, remember the null hypothesis was that the mean of the average gas mileage of these cars was 40 miles per gallon. So there we go. We got 40 right in the middle. Now, what else do we have on here? If you notice all the way over here on the left, if I ignore the second dotted normal distribution, you'll see that there's this little bit boundary right here, and there's this kind of shaded in red, and this little bit shaded in red is said to be alpha. That's 0.01. This represents basically the scenario where I'll end up rejecting the null hypothesis and maybe potentially making a type 1 error. If the null hypothesis was true, it's possible to make a type 1 error. The probability that I make a type 1 error would be 1%, and that would be based on the probability of getting a sample mean that would be this far away from the population mean. What was this distribution again? Remember, this was a normal distribution. It was centered at 40, and its standard deviation would have been 3.1 divided by the square root of 30, because 3 was the population standard deviation, and then we had a sample size of 30. And that's actually what this value is right here. It was 3.1 divided by the square root of 30, and you can verify that's true. So this is this normal distribution right here. It's based on the null hypothesis, and any sample mean below here will cause us to reject the null hypothesis. What kind of sample means are we talking about? Well, I did some math, and in another video, I'll walk you through the math. But I did some math, and it ends up saying, oh, that sample mean would end up having to be something that's less than 38.68. So if you recall, the actual sample mean that we got in our scenario, which I have on this paper here, remember the actual sample mean was 38.9 miles per gallon. Was that so too far away that we would reject the null hypothesis? No, that was 38.9. 38.9 was like right around here somewhere, right? And therefore, our p-value would have been this part, and that would have been bigger than 1%, and therefore we would have failed to reject. Okay, so that's all that. Now let's turn to this dotted distribution. This dotted distribution, oh baby, this guy's interesting. This is the distribution that's reflecting on the truth, right? Let's say, notice that we said here, let's say that the actual gas mileage of this car was 39 miles per gallon. And then this distribution right here, this would have been a normal distribution, right? Now this time its mean would be 39, but its standard deviation would have been exactly the same, 3.1, excuse me, divided by the square root of 30, right? And so this guy right here, notice its center is right here at 39. And now, if this is the truth, if this is the real world, then the probability that I avoid making a type 2 error, the power of the test would be really the probability of me getting a sample mean, again, under 38.68. Now, this time, 38.68 is not being compared to the hypothetical distribution based on the null hypothesis. It's based on, this is the true distribution of mu's, right? The true distribution of the actual, it's not the distribution of mu's, that doesn't even make any sense. This is the true distribution of the gas mileages of these cars, which is truly on average 39 miles per gallon. So the probability they get a sample mean that would cause me to reject the null hypothesis is going to be the total area under the curve where I have sample means that are less than 38.6. So if I was to go in my calculator and say, what's the probability of getting a sample mean less than 38.68, right? Then I could use normal CDF based on this distribution, and it would come out to being this number right here, 0.2879. And why am I just writing it again? I don't even know what I'm doing. But that is actually the area under this curve right here. You can, if you want to throw in your calculator, you can check and let me know. Was I right? Oh yeah, thank you. I was right. Thank you. And so that's the power of this test. Now notice that your power of your test is not super high here. It's only 28.79%. It's not a super powerful test. Why? Number one, our alpha was only 0.01. Number two, our sample size, not that large. It was just at the boundary of us being able to use the normal curve for a sampling distribution. And finally, it's not that big because the true value of the mean was, the true average was not a whole lot less than what was hypothesized. It was, in fact, only 39 versus the null hypothesis, which was 40. So let's say we played with some of those things. The first thing let's play with, let's just say we took more data and we simply had a larger sample size. Now, the power of the test is going to go up to, as you'll see here, 56.84. Why did the power of the test go up? Well, once again, the truth was supposed to be 39, right? There's the mu. But what really happened here is what happened to the distribution when we increased the sample size from here to here. What happened? Oh, look, it got skinnier. Ooh, the sampling distribution of the sample mean standard deviation went down to 0.4. Why? Because remember, it's always the population standard deviation divided by the square root of n. In this case, that would be 3.1 now divided by the square root of 60, right? So that decreased the amount of variation, that made each of the distributions more narrow, and it actually shifted upwards what kind of sample means would cause us to reject the null hypothesis. In this case, we would reject if it's less than 39.069, right? And so the probability of getting something less than 0.69 would now be based on this distribution. It's again a normal distribution with a mean of 39, but its standard deviation is even lower. It's 3.1 divided by the square root of 60 instead of the square root of 30. And so now we actually have a more powerful test because the entire distribution squeezed around closer, and it made it at least for us in this particular case, more likely to find something that would end up getting rejected. So increased sample size decreases variation, makes it easier to reject. All right, so once again, that's nice. One way that we could have increased power is by just getting more data. Another simple way would have, in some ways, be less desirable for the Hyundai company, but that would be to just change our level of significance. Remember, Hyundai, they would really be worried about a type 1 error. They don't want people to all of a sudden say, oh, your car's got a gas mileage that's lower than what you said when it really isn't. They care about type 1. But if the truth is that the alternative was the truth and the null hypothesis is false, then it would have been better in this case to have a higher level of significance. So say we move the level of significance up to 0.05, right? Well, in this case, we'd actually still have our good old 39.069 as our rejector. What is it? Is it really say the same? Wait, hold on a second here. Oh, yeah. No. What am I trying to say? I'm so dumb sometimes. The rejector went up. So, oh my gosh, I'm trying to do this video too quick. The rejector went up. Why? Because the boundary got shifted up, right? Now, instead of having the boundary region based on 1%, it was just actually the reason why I got thrown off there is just coincidentally is like this, it ends up being like very, very similar to if I just had the sample size of 60. Sorry, I just confused myself there just a little bit. But anyways, by increasing the level of significance, we made it so that with the same standard deviation of the sampling distribution, which was 3.1 divided by the square root of 30 now, we end up choosing to reject the null hypothesis. So there's more sample means based on the null hypothesis that would cause us to reject. And so in this case, our true distribution would have been centered at 39, would have had a standard deviation of 3.1 divided by the square root of 30, because remember, we're back to the sample size of just 30. But that level of significance of 0.05 does create more situations where we're going to reject the null hypothesis, increasing the power of our test to 54.85%. Notice that increasing the sample size, all things being equal, made it a little bit more powerful than actually just increasing the level of significance. So which would you prefer to do? Get more data or just increase your level of significance? You probably should just go ahead and get more data. Let's look at one more scenario. Remember, our baseline was when mu was 39. We only had a power of 28.79% when the sample size was 30 and alpha was 0.01. Now let's change not the sample size and not the level of significance, but let's actually change the effect size, right? And remember, the effect size was this difference between the hypothesized value and the actual truth. And let's kick it down to 38, right? And let's say that the truth was even more extreme than 39. Before, remember, we had a normal distribution centered here at 39. Now the true distribution is centered down here at 38, right? So this would be a normal distribution with a mean of 38 and still the standard deviation of 3.1 divided by the square root of 30, right? Centering this distribution further down greatly increases the power of our test because now the truth is more extreme away from that null hypothesis over here. Our effect size went up to 2 or -2, depending on if you care about the direction. And the power of our test jettisoned up to 88.64%, right? And so this really increases the power of a test. The sad part is, in reality, this is not really under our control because we can't control what the truth is. But we do know that this test is actually much more powerful if the alternative is very true. Remember that, in other words, the alternative, which said that mu is less than 40, let's say that mu is really less than 40. That makes our test much more powerful. Let me pull back the curtain. In fact, like I said, I bought a 2012 Hyundai Accent. I bought it brand new. And eventually, Hyundai, it came out that the car did, in fact, have highway gas mileage that was less than 40 miles per gallon. And I did a Google search just to try to show this to you. And I Googled this today. And in reality, mu was about 37 miles per gallon. And now that's what's advertised. If you go and you look up a 2012 Hyundai Accent, Google it yourself, you'll see that the highway gas mileage is only 37 miles per gallon. And so let's say that was the truth. That is the truth. And in fact, this is the true truth now. This we have good reasons of believing is in fact reality. How powerful would our test been just at a sample size of 30 at 1% level of significance? Well, let's say that 37 was actually 37.4, that rounded down to 37. Then even at 37.4, the power of our test would now be 98.83%. Why? Because the truth was all the way down here. This is the true value for mu, and this is just what we hypothesized it to be, and that's what that little zero kind of means there. Since there was such an extreme difference, there was that mu was really less than 40. It was all the way down here at 37 miles per gallon, not 40. It should have been very easy to reject the null hypothesis and avoid making a type 2 error. In fact, it's nearly impossible, almost any data. And actually, as it turned out in reality, the reason that Hyundai had the wrong gas mileage is because some reason they were actually performing the tests wrong. It wasn't they weren't lying with their statistics. There was actually something wrong with their data. There was bias in the test that had to do with a kind of response bias, that there was inaccurate data that was being used, and that's why I ended up having the wrong stuff. So anyways, that's the key things that I want to show you about the power of a test. What were the 3 things that we talked about that affect the power of the test? They were the level of significance, which is completely under our control. If you want to really avoid making a type 2 error and have a very powerful test, make your level of significance very large. You could always increase your sample size as much as it's feasible and cost effective. Go ahead, get more data. You'll have a more powerful test. You'll be able to detect if the null hypothesis is false. And now, hypothetically, if the effect size, if you want to be able to detect an extreme effect, it should be very easy to reject the null hypothesis. But remember, in reality, the effect size is always something that's also kind of hypothetical. The only things that are definitely certain are changing the effect size and changing the level of significance. The truth is what the truth will be. We could hypothetically say what the power is based on this hypothetical value of the truth, but that is not the truth. It's just this hypothesis. Guys, I hope this was helpful. Thinking about type 2 errors can be very tricky. Hope you got the main concept down. I will post another video where we actually more thoroughly and carefully do some of these calculations just to hopefully you can more deeply understand them. But that's the key essence of things. I hope this helps. I'll catch you on the flip side.